Swayam Prabha. Digital India. Educated India.
This lecture is continued from the last lecture. In this lecture, we'll be taking the example of mechanical system and how we can find the linear relationship between the input and output. Here we'll be considering the example of gear press system, and we'll find the relationship between the rotational angle of the shaft and applied torque. And then we'll shift our attention to the block diagram concept, which is very important for the aircraft system. Because in aircraft, there are multiple subsystems are connected in series or parallel, and how the overall transfer function can be derived between the different inputs and output. Then we'll conclude the lecture. In this lecture, we'll be finding transfer function of a system. As you have already mentioned that we'll be dealing with the positive values of time, so we'll replace 0 plus by 0 as we mentioned. We'll be dealing with positive values of time. We'll replace 0 plus by 0 in all relevant applications of Laplace transform. Let's consider we have a system, linear system, in ordinary differential equation form. An d n y of t dt n plus a n minus 1 n minus 1 y of t dt n minus 1 plus a1 dyt dt plus a0 y of t equal to, we have input function as well, bm d m u of t dt m plus m minus 1 u of t dt m minus 1 plus dot dot plus b1 dut dt plus b0 u of t. So this is, we can assume this is the ODE equation or in differential equation. And for simplicity, we'll assume the initial conditions. For simplicity, the initial condition will be assumed to be 0. For simplicity, we assume the initial conditions for the input ut and its time derivatives and the output y of t and its derivatives are zeros. In Laplace domain, so if you have these conditions in Laplace domain, in Laplace domain, we can take the Laplace transform of the equation. Let me write this equation number 1. In Laplace domain, if we apply Laplace transform to equation 1, we have Sn n y of s plus Sn minus 1 an minus 1 y of s dot 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 plus s a1 y of s plus a naught y of s equal to, we can write Sm bm u of s plus Sm minus 1 bm minus 1 u of s dot plus SB1 u of s plus b naught u of s. And if you take y is common from the first equation, from the left hand equation, and u is from the right hand equation, we can write Sn n plus Sn minus 1 an minus 1 dot 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 plus SA1 plus a naught y of s equal to, we can write Sm bm Sa minus 1 b minus 1 dot 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 plus is b1 plus b naught us. And from this we can write y of s by u of s. We can write ys of s and bs. We can write Sm bm plus Sa minus 1 bm minus 1 dot 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 plus SB1 plus b naught divided by, we can write Sn n plus Sn minus 1 n minus 1 plus SA1 plus a naught. So this is, we can write in GS equal to this. So this actually this is the transfer function as you have done before. This is basically transfer function basically the relation between the Laplace transform of output divided by Laplace transform of input. Laplace transform of US divided by Laplace transform of US. So this is how we define the Laplace transform, transfer function of a system, the linear system. Now we'll take an example how we can come up with the same concept for some system. Let me go through some basics. Let's go with the rotational mechanics of a system. Rotational mechanics. If you have some spring which is connected to some wall, some spring, and this spring is a rotating spring. Let me write, this is the rotating spring. And the rotational angle is, let's assume, theta. And due to the rotation, we are having some torque T. Let's assume the torque is T from this spring. The spring is actually rotating like this. And the total torque generated from this spring, we can write T equal to minus K theta. So here K is the spring constant. Spring constant. And if you have another example, the wall, this is the wall, and to this wall, a damper is connected, and this is actually, you can say, rotational damper. And the rotational angle is theta, and the torque, let's assume T again. And if we assume the damping coefficient B, which is greater than 0, here K is greater than 0, spring constant if you assume. So in this case, the total torque from this rotational damper, we can write minus B theta dot. And if you write the rotational spring, if you have rotational spring something, and something is connected like this, and not rotational, this is rotational friction, if you assume rotational friction, and if you assume the G is the some inertia, rotational inertia, if you assume J, and if you assume the angular motion of theta, and due to this the torque generating T, for example, then total torque from this rotational friction we can write minus B theta dot. So this is how we can come up with the torque from this kind of systems. Now let's extend to another system. We have some gear flow system. And for this system, we'll find the transfer function. Okay, here also you can find the transfer function. If you apply the Laplace transform, you will have, if you apply the transfer function, Laplace transform, you can write minus B theta of S. So it is basically, we can write, this is equal to, we can write theta of S divided by T of S, we can write something like. So this is how we can write the transfer function for this system, and this system also can write. Let's have this example gear pulley system, and let me draw the figure. So we have one gear, primary gear, and the shaft, and the rotational angle is theta, and due to this rotation we are also having some torque T1, and let's also assume the N1 be the gear ratio for this teeth gear ratio of the gear. And we have another gear, bigger gear, and N to be the gear ratio for this system, and there is a pulley connected like this. This is the rotational in like this, and this is connected to a rotational inertia, the inertia J, and again this is connected to one spring This is related to 1. And this is the spring constant K. And we are assuming the rotational friction B is here. And from this rotation, we are getting theta 2 is the rotation, let's assume. And we are getting the torque T2. So this is the system, and we'll find the transfer function for this system. So here I can say T1 be the input torque and output be the theta 1. Let's assume this is the angular displacement. And we'll find the relation between T1 and theta 1 for this system. T1 will be the torque, input torque, and theta will be the output. So we'll find the relation between T1 and theta 1. So let's go. From this system, you can find the relation T1 by N1 equal to T2 by N2. This is the fundamental equation from the mechanics. And from this, we can write T2 equal to N2 by N1 into T1. Let me define this equation number 1. And we have another equation from the angle and teeth gear ratio. We can write N1 theta 1 equal to N2 theta 2. And from this, we can further write theta 2 equal to N1 by N2 theta 1. Let me define this equation number 2. Now, also from the constant equation, or I can say torque balance equation, we can write J theta 2 double dot equal to T2 torque minus B theta dot minus K theta 2. So this is the second equation. We are writing this equation for the second system here. This second system, we are writing this equation for this system. So now, let me define this equation number 3. From equation 1, 2, and 3, we can write, if you substitute in place, because what is our end goal? We have to find the relation between T1 and theta 1. This is our end goal. We have to find the relation between T1 and theta 1. So, but the system is coming out to be relation between theta 2 and T2. So we have to convert this equation into theta 1 form. So if you replace theta 2 and T2 variables in terms of T1 and theta 1, we can write the equation in terms of T1 and theta 1. So now, like J, in place of theta 2, we can write this expression. So we can write N1, N2, theta 1, double dash, plus, we can write B into N1, N2, theta 1 dash dot, double dot, double derivative, and we can write K N1, N2, theta 1 equal to, we can write in place of T2, we can write N1, sorry, which will be N2, N1, and T1. So now our equation has been converted to in terms of T1 and theta 1 form. Let me define this equation number 4. If we apply the Laplace transform, we can write equation N1 by N2. We can write J S. Let me first write take the common both side, and B theta 1 dot plus K theta 1 equal to N2 by N1 T1. Now if we apply Laplace transform to this equation, Laplace transform to the above equation, we can come up with the equation N1 N2 J S square. This is second derivative, so S square will come into picture. Theta of S plus Bs theta 1 of S, and K theta 1 of S equal to N2 by N1 T. I can write capital T 1S. Now we can come up with the theta is the output and T is the input here, T1. So I can find the relation between T1 and theta 1. Theta 1 is N2 by N1 square divided by Js square plus Bs plus K. So this is basically our transfer function. So we can write Gs equal to theta 1 is by T1 is, this is basically transfer function. This is the transfer function basically relates between the input and output. And this is a very important example, and we'll be following this way for the other system as well, for the aircraft system. Let's look some concept of transfer function, how we can find the transfer function in different structure. If there are different multiple system in the loop, how we can find the transfer function for the overall system. So this is the part of the block diagram. So this example, motivational example, how we can find the transfer function for a system. And okay, let's go with the block diagram part. What we have learned till now from this part and the previous lecture. So we have, if you have system G of S, and if you assume we have input to the system by U of S, and if you assume the output Y of S, so we can find the relation Y of S. From this block we can write G of S, U of S. If you consider, okay, one thing we need to say that U of S can be output of another system, because in this case U of S is the input to GS, but US can be output of another system. Here U of S, here Y of S is the output from this system, and similarly U of S can be output of another system. So if you have system, let's assume we have another system H of S, and let's assume the input to this H of S we can write, let me write WS, and from this block let's assume we have US is the output from HS, and this US is going to be input for this block G of S, and the output from G of S we can write Y of S. So from this we can write W of S, we can write the input to the entire system, we can write G of S, and H of S we can write. We can multiply this block transfer function. This is a transfer function which relates between the WS and US. This is a transfer function which relates between the YS and US. So if you have something like this kind of structure, we can multiply the block transfer function like this, and the total response from the system will be same as ys. So this kind of connection we call the transfer function are connected in series form. Now, let's look another structure. Suppose we have system. We have system G of S, and we have another system H of S, and both this block or both the transfer function are relaxed by U of S. So this U is going to both the block, both the transfer function, and the output of the individual transfer function are going through some summing point. If you assume this summing point, so I can write plus plus, and the output of this block is, let's denote y of s. Then we can write, if you want to write the relation between ys and us, we can write in this way. Us can write g of s plus h of s is giving the output y of s. So if you have something this kind of structure, we can write in this form. Okay, now let's look another structure. As you have done in the beginning of this course, how to find the transfer function for the negative feedback system, because if you remember, we had example on how to control the speed of the aircraft. So we have used the negative feedback. Now, if you have system something like that, how we can find the transfer function for those kind of systems? If we have the following block diagram, like suppose we have one summing point here, and to the summing point we are having some input here, and we have in forward loop we have one transfer function c of s, and this is my output from this block y of s. And in feedback, if you assume one transfer function h of s, and if it is h of s, basically h of s in the practical life maybe sensor some kind of systems. It may be the sensor we use in the aircraft, and this is my negative feedback loop, and it's negatively going, and this is the positive and this negative, and we have bs. So bs is nothing but error actually. And let's also assume the output from h is, let's assume a of s. So I think the block is now complete, and from this block we can write is, from the block we can write, from this block we can write is equal to hs ys, and bs we can write us minus as, we can write. And also from the in the forward loop we can write y of s equal to gs bs, because ys I can write gs multiplied by bs, we can write. So now from here, G of S in place of BS, we can write this expression US minus AS. And from this, we can write G of S, U of S minus G of S. And in place of AS, also we can write this expression. So we can write GS into HS YS. And from this, we can write YS plus GS HS Y of S equal to G of S U of S. And from this, we can find the relation between the YS and US. Because in transfer function, we generally find the relation between the input and output. This is also one transfer function. This is also one transfer function. But if you come up with the complete one, can be a transfer function also. Let me do it, then I'll explain. So I can find the relation between the YS and US. So from this, I can take common YS, I can take common 1 plus GS HS equal to, I can write CS US. And from this, further I can write YS output divided by input. This input is the system input, that complete input to the system, the whole overall input to the system. So I can write G of S divided by 1 plus G of S H of S. So this is the transfer function of the transfer function of a negative feedback system. Now you can write the same way, if instead of negative, if you have positive sign, what will happen? So this is, you can try, if it is positive, what will happen? This concept will extend for aircraft system in the next lecture, how we can come up with the transfer function of a rotational motion of our aircraft. And from after finding the rotational motion of the aircraft, transfer function, we'll moving forward how we can design the control autopilot for the same. So let's stop it here. We'll continue from the next lecture.